Okay, so sorry, I need to share my screen. Chapter 9, hydrogen in land mobility, and Chapter 10, and sea, air, and sea mobility. As I mentioned last week, I just like to share with you what kind of activities is going on. There's one article released, I guess, May 26. It was 2 days ago. Well, last week I attended this Netherlands hydrogen exhibitions with the two PhD students. It was in Notre Dame. Again, I would like to emphasize there are so many display of the hydrogen-related technologies from all over the world. Korea, we also had one. We had a booth by the Hyundai Automotive and Doosan Fuel Cell and Miko Power and many technology. And the point of this article is that we call it WHS 2025. This is was the sixth the world's largest international hydrogen exhibitions and conference, and they share all the technology and then try to work together, move toward the hydrogen society. So again, this is a really new, relatively new energy industry. We have to change our concept of a conventional concept toward this new energy source. So you, as an engineer of Hanyang, master degree or PhD degree, no matter what research you guys do, is very important to understand the energy source, especially this hydrogen. This is the one article I like to emphasize. And back to our brief course note, we had chapter 9 and chapter 10. Well, since this area is a quite new area, is worldwide, new technologies coming out. So to study all these subjects, the best way is to go into Google search, looking for what is the new news. So let's get back. Let's go to again. Today I like to go through the searching each technology and application as mentioned here. Fuel cell electric vehicle, which we already covered that. Now we like to cover more typical applications such as trucks and bus, which which need a much larger hydrogen gas, hydrogen energy than just passenger vehicles. Okay, so we can simply type here. hydrogen, they are trucks and buses. Okay, well, as you notice that the way they present all the information was pretty much based on the AI searching, so we can get a lot more and well-organized informations. Well, hydrogen trucks and buses, and the Google give us some very well documented, something like that. And then we can, of course, we can get this is all the AI overview. Now, let us go through all the points this Google search giving us. Hydrogen trucks and buses, also known as the fuel cell electric vehicles. The fuel cell electric vehicles is certainly the trucks and buses are very typical applications. Offer zero emission. Well, this is the point, the zero emission alternative to traditional diesel vehicle. See, we had so much the CO2 emission problem and climate problem. The main blame went to these trucks and buses. Trucks and buses use the diesels, and they produce so much the CO2 emissions. So anyhow, the trucks and buses, we all need to replace the energy fuel system with the hydrogen. So offer zero emission and these vehicles use hydrogen fuel cells to convert hydrogen into electricity, which then power an electric motor and resulting in only water as a byproduct. Well, this is a very well-known fact. By now, we should know. And zero emission, this is nothing new. Hydrogen fuel cell will generate nothing but zero emissions and emit only water, significantly reducing the emissions. And also longer ranges. Hydrogen fuel cell can provide a longer range than battery electric vehicles. Certainly for these types of trucks, we can use the battery like the passenger vehicle, but in case of a heavy truck, battery electric vehicles cannot give us long enough ranges. So in these truck and buses, to get the longer ranges, hydrogen fuel cell is much better than batteries. So this is an important fact why we prefer hydrogen than battery. Rapid fueling, hydrogen refueling can be faster than battery charging, providing more significant refueling experience. What it means is that if we charge the battery, then it takes still hours to charge them. Well, recently there are new technology, new fast charging battery technology, but that still needs to be confirmed and verified. And even though it is successful, the battery charging is still takes time, much longer than hydrogen. Hydrogen refueling is very similar to the time is very similar to a previous diesel fueling time. And the potential cost saving, transitioning to hydrogen-powered vehicles could lead to a significant long-term cost saving due to reduce the fuel cost and maintenance. Well, this is not the current situations. This is the potential cost savings with the assumption that we generate hydrogen using the renewable, such as the wind or solar cells. But we are moving toward that directions. Now, typically, Hyundai's hydrogen-powered vehicles, Hyundai, they have a model called Exient. This become very popular. Well, we don't see them in Korea, but this Exient is popular in Europe. So Hyundai is a major player in the hydrogen fuel cell vehicles market, producing the trucks and buses. Now, Exient is the world's first mass production hydrogen power heavy-duty trucks, giving us the range of the 400 kilometers, which is very long enough for the heavy trucks. Elect City bus is designed for both cities and intercity travel. And Hyundai is also working on improving the efficiency. See, Hyundai has a very world-top technology of fuel cell. The fuel cell certainly applied to Nexo and also applied to buses and Exient. So the Hyundai is the one of the company which leading the fuel cell technology. So other manufacturer and deployments, say Wright bus and the Solaris bus, Lamborghini and Volvo trucks, and DHL, you know the DHL, the transport logistics, they are using the hydrogen power, the trucks. But still there are a lot of challenges and consideration, and some issues remain to be solved. One very typical, the problem is that infrastructures, lack of hydrogen refueling infrastructures is a really major barrier to the widespread adoption of hydrogen vehicles. And so we need to have a fueling stations, and which costs a lot more than conventional gasoline types stations. So it's like the chicken and egg game. To have a we don't have a much infrastructures to, for this hydrogen truck get popular, but the to get more the hydrogen trucks and this, we need more hydrogen stations. But again, the hydrogen station costs a lot. We need more buses and trucks. So that problem, at first need to be solved by some national politics or some incentive. So, okay, the cost of hydrogen fuel cell technology can be more expensive than traditional diesel or gasoline vehicles, although costs are expected to decrease with increased productions. So currently, they are still very costly. Hydrogen production. Hydrogen is not much, sufficient. And producing hydrogen in a sustainable way, again, using the renewable energy source, is crucial to ensure all environmental benefits of hydrogen vehicles. So conclusion, hydrogen trucks and buses are emerging as a viable and environmental friendly alternative to traditional diesel vehicles, offering the potential for zero emission and long range and so on. Well, but again, as we went through, we have several problems to be solved. If we go to well, there are still a lot of debate whether this hydrogen energy will be is a good choice or we're going to be successful. There are still a lot of things to be done. Well,
the International Conference on Green Hydrogen exhibition, hydrogen-powered long-haul buses and trucks are showcased as part of pilot projects by the Automotive Research Association of India. With 40 vehicles under evaluation, these tests in different climates aim to optimize hydrogen systems for heavy-duty transport, pushing India closer to green, sustainable transportation. Tapas Bhattacharya reports.
Hydrogen is the new buzzword when it comes to India and its way of becoming net neutral by 2070. The National Green Hydrogen Mission is a huge step for the country, and the Ministry of New and Renewable Energy is working in tandem with the private players. And to talk more about that, I will be the Joint Secretary, Mr. Yadav.
Well, India is the one of the country which actually do not have a much natural resource. Very similar to Korea. We don't have a much natural resource like the oil and gas. And India, the same situation in India. And so the India also government-wise and industry-wise, they are pretty much pushing toward the all the hydrogen-related technology. Bus is one of them.
Tell us, we are talking about the green hydrogen mission. We're talking about how to take the country forward when it comes to renewable energy. It's expected to play a major role. How does your government see this?
Electrolyzers will play a key part in this generation of green hydrogen. And under the National Green Hydrogen Mission, what we've done is that we have awarded 3,000 megawatt capacity of electrolyzers. So this capacity has already been awarded. We'll be supporting this capacity per annum for a period of 5 years. So the cumulative capacity that we'll be supporting will be 15,000 megawatt of electrolyzer production capacity. Now these plants are at various stages. Some of these plants are at advanced stage of commissioning.
Private-public partnership coming in and with the ministry giving them that boost. That's a huge point. With India have already stated that by 2070 they will be net neutral. Do you believe that we are on course to meet that challenge?
Yeah, right. So in addition to what I told, electrolyzers, now we have again have incentives for production of green hydrogen. Till now we have awarded around 412,000 tons capacity of green hydrogen production. And we are also looking at different use cases of green hydrogen and its derivatives. So we are launching pilot projects, for example, in mobility sector, how to use green hydrogen in heavy duty automobiles, buses, trucks.
So Yadav has pointed out, the Joint Secretary said that the ministry is going full throttle when it comes to the green hydrogen mission, making sure that India is on course to achieve the net zero target by 2070. With camera person Monty, this.
Okay, as you can see that the India has a plan to be really net zero, no emission by 2070. Well, the India government-wise, they are making such a big effort to move to this new way of energy. So I believe that the hydrogen is never giving up chances for India, also Korea and other countries as well. Okay, so you can find a lot of different research and relate to trucks and buses, and each country will have a very different, I mean, very widely developed all over the world, and well, you can find those information very easily. Okay.
Just recently, the U.S. Department of Energy set a world record with a hydrogen-powered truck that traveled a staggering 1,806 miles on a single refueling. That's right, no stops, no emissions, and a glimpse into the future of clean transportation. Hydrogen's impact isn't limited to trucks. It's being used in cars, buses, planes, and even data centers. But today, let's look into how this achievement fits into the broader landscape of hydrogen fuel cells, their applications across industries, and global economic trends driving this technology forward. All of this on today's Hydrogen Podcast.
This is the 2025, this year. There's a news saying that new hydrogen buses and trucks are developed and covering how wide ranges it can run, and all the most of the news is introducing new technology, and we are ready to move to a hydrogen society, and so it is a kind of a situation that each country, each technology, we are getting ready to jump to a new era. But I believe that sooner or later this will be a game-changing technology that who would be the winner? Well, those who will be the winner is the one who prepared in advance. Otherwise, we cannot suddenly get a technology. So we have to prepare ourselves to be the winner. I mean, I just picked the one of some of the website and YouTube, but the you can see you can find a lot of further and better informations. Well, it happened to be India again. This is a Tata. Tata Motor is one of the biggest company, automotive company in India.
Right, Thomas. Stay with us. In fact, we're telling now to more news coming. Tata Motors has commenced trials of hydrogen-powered heavy-duty trucks in India, marking a significant step towards reducing emissions in long-haul freight transport. The project funded by the Ministry of New and Renewable Energy under the National Green Hydrogen Mission aims to assess the feasibility of hydrogen as a clean fuel alternative for commercial vehicles. The trial was launched in New Delhi in the presence of Union Minister of Road Transport and Highways, Nitin Gadkari, and Union Minister of New and Renewable Energy, Prahlad Joshi. It will involve 16 hydrogen-powered trucks operating on key freight corridors, including Mumbai, Pune, Delhi NCR, Surat, Vadodara, Jamshedpur, and Aligarh, which is expected to last up to 24 months.
Okay, well, this news was released, when was it? It was just 2 months ago. Well, I personally, I went to India and give a talk and discuss with Tata. It was about 1 year ago. Now you can see that this year, how they move and how they develop the hydrogen car. You can see that how quickly the automotive manufacturing company and government are developing and moving very fast to the this new hydrogen technology, such as trucks and buses. Well, like to emphasize that hydrogen, I mean, for the application of vehicles, passenger vehicle is not so efficient with the hydrogen, but trucks and buses is a much better application compared to a battery. So the hydrogen application tank will go into very fast to trucks and buses. This is no doubt. There is some the reason for that, many reasons for that, which we already review in the Google search. Okay, so I like to just share the this type of trend, and so this is the point: hydrogen trucks and buses. Now there can be some hydrogen train. In France, there is a very famous company which is like the Hyundai Rotem in Korea, and Alstom announced that the world first hydrogen powered passenger train. Well, when was it? When was this was released? I'm sure this is the not long ago. As you can see that. Oh, by the way, Alstom is the company from which we got the all the technology of a high-speed train like the KTX a long time ago. Now we are producing the high-speed train better than any other company. So again, the Alstom is a French company, and we got the older technology. Actually, we bought most of a train and technology together. That was I don't remember, but it was about the 20 or 30 years ago. But anyhow, the Alstom start to produce hydrogen-powered passenger train. Actually, the Hyundai Rotem do the same thing, hydrogen-powered train. I'm sure we can get the similar. Well, hydrogen fuel cell tram or train. Well, right now is a tram. It was released last year, Hyundai Rotem, and also Hyundai Rotem is
trams disappeared.
Rotem is the one company which is the kind of a sister company to Hyundai Group. But again, they are producing a lot of technology related to hydrogen fuel cell and also for the train, etc. As I mentioned, the last week of the Netherlands hydrogen conference, Hyundai Rotem was the one of a company. They showed all the technology, by the way. So anyhow, let's watch what they are saying.
Years ago, due to new urban planning, but now green tram technology is attracting global attention.
우리는 세계 시장 진출을 위해 2009년부터 트램 연구 개발을 시작했습니다. 사람과 도시와 서로 공존할 수 있는 트램을 만드는 것이 단 하나의 목표였습니다.
In a short time, Hyundai Rotem began connecting the globe. Their tram technology has proven to be world-class. The company saw innovation as vital for the tram to be sustainable in cities. They found the answer close at hand.
평소에 수소전기 자동차에 대한 긍정적인 생각을 가지고 있었고요. 지금은 정말 만족하면서 타고 있습니다. 버스나 열차 같은 대중교통에도 수소가 빨리 도입되면 좋겠다는 생각이 듭니다.
Began researching hydrogen power 30 years ago, recognizing its potential as a clean energy source. Now the entire Hyundai Motor Group is bringing hydrogen fuel cell passenger cars, trucks, and buses to the global market. Hyundai Rotem also has hydrogen facilities and began developing hydrogen fuel cell trams in 2019. The innovation has begun. Hydrogen fuel cell trams have three main advantages as a sustainable means of urban transportation.
첫 번째로 수소 전기 트램은 도시 경관을 아름답게 유지합니다. 기존의 트램과 달리 가선이 필요 없기 때문에 시각적으로 매우 쾌적하고 도시 개발에도 유리합니다. 두 번째로 지속 가능한 교통순환입니다. 수소와 산소가 결합해서 전기를 발생시키고 운행 중에 온실가스 배출이 없습니다. 두 번째로 수소는 많은 에너지를 저장할 수 있기 때문에 한 번의 충전으로도 장거리 운행이 가능합니다. 수소 전기 트램은 최적의 도시교통 수단이라 할 수 있습니다.
Although the project was going well, they encountered a number of unexpected challenges.
수소 기반 전동 차량에 대한 기준이 없어서 많이 힘들었죠. 먼 거리를 이동 충전해야 하는 경고로 상황까지 여러 가지 어려움점들이 많았습니다. 그때 함께 고생해준 팀원들에게 많이 고맙죠.
In 2021, they succeeded in developing the concept and began working on commercializing the prototype. A new era of the world transit industry dawns. Hyundai Rotem needed a brand new design for the development of the hydrogen fuel cell tram.
트램은 생활의 일부분이자 또 도시 기능의 일부분이라고 봅니다. 심미적인 측면도 물론 중요하지만 문화 편리하게 이용할 수 있도록 사람 중심의 디자인입니다.
Final design achieved remarkable success by winning the 2023 IF Design Award.
우리만의 디자인이 아니라 세계가 그나마 그 디자인을 해낸다는 것은 매우 국내 철도 업계에서는 최초의 국제 디자인 어워드 사례라고.
They quickly reached the final testing phase of the project using Hyundai Motor Company's technology.
무엇보다 안전이 최우선입니다. 트럼프의 목표는 2,500km였는데 우리는 그 2배인 5,000km를 달성했습니다. 2024년에 시험 운행 단계까지 마치면서 공식적인 수소 전기트램 개발 프로젝트는 성공적으로 완료되었습니다.
For Hyundai Rotem, this begins a bold new journey. The company believes that the most important is the voices of actual users. This is their final stage of research and development.
우선 환경에 미치는 영향이 거의 없다고 해서 쾌적하게 느껴졌어요.
조용하고 편안하고 안전하다는 느낌.
It's a really exciting project and a really important way for us to turn our transportation net zero. So congratulations on this fantastic demonstration.
Hydrogen energy embodies the value of fairness for all, putting humanity on a contract. They wrote, hydrogen fuel cell tram delivers sustainable innovation for all.
While the tram is not a train, but this is the very similar to train in terms of rails and But tram is the mostly in the urban city purpose, but this can be easily expanded to a regular train, which you can see here. So like to emphasize that Hyundai Rotem has been developing this technology for more than 10 years. Now they are demonstrating and ready to produce for the market in Korea and also a market in globally. The India again, as you can see that will be a great market. India environmentally they need to be very much. They need to be clean. So hydrogen is the right source and right directions. Okay, so the Alstom is the one company who can produce the hydrogen train in globally in France, and Rotem is the one domestic company, Korean company, who can produce the hydrogen train or tram. Okay, that's what I'd like to emphasize. Well, again, you can go through many different applications, and like the buses on the roof, you can see that lots of hydrogen tank. Of course, you need a tank similar to the battery for the electric vehicles. And the train, see, you need to have a hydrogen gas stored. And this is the very typical storage tank, just behind of the driver and passenger. And you can see the hydrogen truck. And this truck, this hydrogen tank is much bigger than regular passenger vehicle. The hydrogen tank for the passenger vehicle is about the 50 to 70 or 80 liter for each tank. But the hydrogen tank, each one will be about 250 to 350, which is a lot larger than conventional the passenger vehicles, as you can see that. And sometimes, this is the technology-wise, similar to passenger vehicles, but the capacity-wise, like the hydrogen tank and hydrogen fuel cell, will be much larger than passenger vehicles. Well, we are doing some homework how to estimate energy for the humanoid to estimate the hydrogen tank and fuel cell capacity. Well, this procedural concept can be equally applied to how to design the train, how to design the trucks and buses. So do not just focus on the humanoid, but again, the technology or procedure can be extended. So simply, technology-wise, we need a tank storages, and then how to locate the tank like this, and then design or determine the specifications of fuel cells. Okay. Oh, by the way, this is the hydrogen fuel cell appearance, and you can see that which is not small. This is also heavy stuff. and kind of a bulky stuff. And this is a fuel cell. And we went through the how it works. It is it consists of many multi-stack so that hydrogen gas in and electricity out. So this is a energy conversion system. This is another pictures of showing. Let's say hydrogen tank for the trucks and buses. You can see the real dimension of a hydrogen tank. And as you can see, Hexagon, by the way, is the one of the largest company who can produce the hydrogen tank. Hexagon Cross. They've been actually the Hexagon, the fuel storage system for buses, fuel storage. This is the hydrogen gas, and the we are looking at the hydrogen tank for hydrogen buses and trucks. Okay, and the it's a huge, and of course it needs to be safe and needs to be very cost effective and lightweight. Why lightweight is important? Well, it's a Type 4. Type 4 is the inner liner is a plastic, and which can make the tank much lighter than conventional metal type liner. And this is the typical arrangement of a storage system, hydrogen buses and Hexagon Purus. This is the brand name of the Hexagon. Yes, they are really expanded their the productions and markets, and as you can see that the rail, I mean the train and trucks, and for long distance travel, and they are developing some hydrogen tank, and has to be flexible and modular. Flexible and modular means that they cannot make the one tank which is enough for all hydrogen gas. They needs to be modular like this, 1, 2, 3, 4, and 1, 2, 3, 4, and you can see this kind of arrangement. And the interestingly on the roof, they made a 2 big one and 2 smaller one, so that these 4 tank can be located on the top roof safely. Where vertical seating and horizontal seating, the location is also very important. Well, truck, there are many different types of the shape and purpose. Medium heavy truck, and they have some typical arrangement and the size. And again, we call it Type 4, which has the plastic liner. And if we go there, and they have all different types of modular, flexible, and you can see modular 1, 2, 3, 4, 5, and then as many as we can. And the lightweight is achieved by the Type 4 and the carbon fibers. And as you can see that since it's the modular, how you can see that you can see the older pipe, I mean the tube. This is the tube go in, I mean hydrogen gas travel, transport. Okay, we are back, and I need to record our class again, but it's okay. Okay, so back to the hydrogen tank, which are produced one of the largest hydrogen tank producer in the world, is Hexagon. Hexagon, they produce all different types of hydrogen tank. They apply to passenger vehicles and trucks and buses and train and so on. And they are all Type-4. Type-4 is the one with a plastic liner, and well, they are saying that it's a modular and flexible, meaning that their hydrogen storage system is adapted to individual conditions, and high fatigue strength and lightweight and certified standardized to be used for the real hydrogen tank. Certainly, they have to be certified. Certification is so critical in real applications and not corroding. Corrosion and fatigue resistant property of Type-4 cylinders is so critical, leading to a high cycle performance and safety first. While their in-house test capacity capabilities for most relevant requirement, hydraulic, leak, burst test, and so on. Well, it is the purpose of reviewing their hydrogen. The tank is the first, this is one of the largest hydrogen tank producers, and the very typical producers. Again, the Type-4. But this is not the only company. We can find a lot of hydrogen tank producer in the world. And this hydrogen storage is the first step, very critical component to be used for the mobility purpose, like the vehicles and ships and trains, and even for the drones and eVTOLs. So anyhow, understanding the characteristics is very critical. We can get a lot of information from this. I will share this website through our Kakao, and we can understand the current status of the hydrogen tank productions. And the well, there can be a stationary storage. Stationary storage means that, like the fuel cell, storage. Oops. Oh man. Yeah. I need to double check why this website is you cannot access properly. Thanks. Hmm. One second. I was about to reboot, and then I pause. I press the maybe. Oh, I wonder, this is the only website we cannot access? Is it because of my computer? No, I don't think so. Maybe I can access it. Okay. Okay. Well, please reply, any students, you have any problems of video and voice and so on, and sharing the screen. Is that okay? Okay. Okay, we are back. Well, I guess the site not accessible at this point, but that's okay. Actually, what I like to emphasize today was that the hydrogen can be applied to a lot different types of applications, train, buses, and the trucks. Now I was gonna introduce the Hexagon, which is one of the largest tank producer and suppliers. Now, when you do a homework, I'm sure that you were assigned to calculate the design very briefly, the size of a hydrogen tank. I would like to share I was going to share the procedure briefly. Okay, make sure the recording and shares. Okay. Now, let's say we have a hydrogen tank, just a cylinder, okay? Just a cylinder like this. And inside we have a pressure. So pressure can be from obviously in the radial directions. And also at the end, we have a sort of a closure end. So there should be some forces applied in the tube axis. So we like to know how much forces are supported by this tube or tank by equilibrium. This is a very fundamental theory, very simple, but the most critical the mechanics, so we need to understand that. Basically, if we cut this part, actually any part, then we will have a certain part like this, right? And all the forces are supported by these cross sections. Let's first take a look at the XL stresses applied to here. I will use the arrow indicate these stresses. And then the forces will be applied to inside this area, all the pressure. So pressure. And I would say this is the sigma 1 is the axial stresses applied on these cross sections. And now we have a ID. This is the ID, and outside is the OD. So pressure is applied to the area corresponding to this inner area with the ID. So the 4 times ID here, I. This is the area where the pressure is applied, and this is the axial force. Now on the left-hand side, any cross section, okay, any cross sections, and it could be here, or it could be here, any cross section. In there, the load is how can this axial load is supported? Well, only the structures we can imagine on this section is this area, right? This area. So the forces applied was supported by this cross section will be sigma 1 times this area, and that will be 4 pi OD square minus ID, right? So this is how we calculate the sigma 1. Sigma 1 is the we can calculate it this way. So I will say P. Okay, this can be delete. P times the ID and the OD square minus ID square. So this is the equilibrium equations. And OD is what? OD is simply ID plus twice of thickness, right? Twice of thickness. Thickness means that this one, this is a T. So the OD is a plus ID plus this is a T and this is a T. And then we can scale them, means that ID plus, well, 4 times T ID plus 4 times something like that. So this one is can be simplified like the P time pressure times, and this one OD square minus ID. Then this the bottom will be the 4 times T, right? And ID plus 4 times T, because this one and that will be eliminate. Then this will be the ID scale, right? Now this T and the T and ID, well, compared to let's say we divide by the ID, so sigma 1 is a P. Divide by the ID. There's only one ID here, and divide by the ID. So 4 times D plus 4, and then ID and the T, right? Okay, so the Well, this can be neglected compared to this one because looking at this one, this is the order of t, but this is t over id, which can be neglected. So let's neglect that. And then, well, you can still use them as they are. Well, we can neglect. So id over 4, what does it mean? Well, id, okay, this can be approximately p times the id 4 and t, and then this one can be id divided by 4 means that r inner radius t and the half, right? This half 4 times is id divided by 2 over 2, and 2 is here, then id over 2 will be ri. So ri means that this id will be twice of ri, or this is twice of r0. Okay, so this is a very simple way, approximate solution, how to calculate the sigma 1. And the sigma 1 is the proportional, certainly the inner pressure, and then have you take a look at this one. What does it mean? R divided by T. Well, R is much larger than T, and divided by half. So let's say this R radius and T is 10 times, then sigma 1 axial stress will be 10 times larger than P. Of course, there is a factor of 2. Now, we can consider the other stresses. The other stress will be like the this way. We can copy here, so that we can take a look at this half circle like this, right? And then again, we have stresses here. We try to have, get an equilibrium of this half circle cylinder, and this will be a certain length. Is okay to have an arbitrary length L. And then remember, we have a pressure P here. So let's say this is the sigma 2. And sigma 2 is the hoop stresses. So the we can have twice the sigma 2. Okay, sigma 2, and then we need to have a cross sections of this this area. How would you do that? Well, this one can be you can say you can use ID and OD, but you can say this what is this? This is a thickness T, which we define here, thickness T times L, this giving us the cross sections. And then we have one here, we have another one here. So we have a 2. And this one will be equilibrium, should be equilibrium, the external force P, which is applied to this half circle. So what's the cross sections? Cross section will be twice of Ri, or this will be ID, and pressure, right? So P2 and the sigma 2 is simply now, well, one thing missing here is the pressure is applied, not Ri times this is the cross sections, right? This is a cross section, so we have a L here, so L here, and then you can see that T and Ri. Well, it's not a difficult derivation, a simple derivation. You can see that sigma 2, this is a hoop stress, is the inner pressure times Ri over T. We have to pay attention to this factor. The R is the much larger than thickness. So it's like the, in a way that pressure is magnified by factor of this Ri over T. And this one is exactly the same. Axial stress will be Ri divided by T, but there is the half. So this is a stresses. Okay, this is a stresses. And if we take a look at the any part of this pipe or tube, let's say we take the some part of this, any part, this one, and this will be sigma. We introduce sigma 2. And this is the sigma 1. And now sigma 1, remember there's inside the pressure, and then I magnify the Ri divided by 2, divided by thickness, but there is a half. But the hoop direction is the pressure times Rit. This is magnified, but there's no half. So this one is the twice bigger than this one. Sigma 1 and sigma 2, and the we need to pay attention that sigma 1 and sigma 2 is the magnified pressure times the R divided by T. R divided by T is sometimes 10, sometimes 20, or so. So how much the sigma 1 and sigma 2 are magnified by factor of this ratio of this pressure. Okay, this is a simple but very fundamental derivation to understand the pressure vessel. Now, another very important point is that how to design the this tank. Well, we can use the if we use the steel material, it's a simple. We can decide the this R and T, right? This R and T. But we usually use the carbon fiber. How can we design the carbon fiber using these equations? Carbon fiber is again all the fiber is goes like that, right? Fiber is running this way. And then, of course, this one this way, same thing, right? Now, the most important point is the angle. Angle is this one. How can we design this angle? Angle again is to define the direction of a fiber in winding. So, what would be the best angle T? That is the most important in designing of this high hydrogen tank made of carbon fiber. Well, most of you guys don't know anything about the carbon fiber, but don't worry, just pay attention to one simple derivation to design the hydrogen tank using the carbon fiber. Okay, so again, we have a piece of plate. Well, this is not the exactly plate. Actually, this is here. But if we pay attention to a very small area, this can be considered as the as a plate, or we can still consider the curvature. But to make the problem simple, we can assume like this. Okay? So this is a stress we just obtained. And also pay very important attention to here. The sigma 2 and sigma 1 has nothing to do with the material properties. As you can see that the pressure is inside and dimensions R and T. That is simply giving us the stresses, sigma 1 and sigma 2. And then again, we like to decide the the fiber direction. Okay, fiber direction. Fiber direction is the something like this T, theta. This one is a theta too. Okay, so we're gonna look at here. Okay, we're gonna look at here. Then we can have a 2D drawing like this. Now, actually, we are assuming the all the load are carried by the carbon fibers. Well, what are the carbon fibers? Well, you can take a look at, you can search the definitions and the typical characteristics of a carbon fiber. But you simply need to understand carbon fiber is very strong in the these fiber directions. Okay, so in the carbon fiber made of carbon fibers are the older load are carried by the carbon fiber, means that this is the only the load we get. You know, this one and that, and all the carbon fiber will carry the load. Okay, then point is that this carbon fiber carries the old, I would say the sigma F. Okay, this is all the identical sigma F and all of the fiber and this cross section. Now the point is that this will be a sigma 1 and sigma 2 with the theta. So we have a certain you know, the angle, and then we kind of decompose in certain direction and giving us in this way, giving us a sigma 2, okay, and this giving us the sigma 1. That is the concept. Now this sigma is not like the vector. A vector will be very simple. Vector, you have a vector, and this is a sigma F, and you can easily transform like this, theta and sigma F, and this is a sigma 1 and sigma 2. If this is a vector, how do we calculate? Well, simply sigma F times cosine theta, and sigma 2 will be a sigma F and sine theta, right? If this sigma F is a vector. But this is not a vector, this is a stress. I would say, so we call F, not the stress, F, some force. Then this equation will work. But the stress, what's the difference between the force and stress is the cross-section area will change again as well. So to make the long story short, simply the sigma 1 will be sigma F times cosine square theta, because there are two different way decomposition. One is the force direction, the other one is the cross-section decomposition. So we have twice of theta, and then sigma 2 will be the twice of sine theta. So this is the simply the sigma 1 versus the sigma 2. So again, all the load are carried by the carbon fiber. This is a carbon fiber. It's strong, and it takes up to a strength of a fiber, and then it giving us the sigma 1 and sigma 2. So this one will be now, as we know, the P times R over T and the half, and this one should be P times R over T, something like that. Now, what we like to do here is what will be the best theta here. So we simply divide by here like this, and then we got this up here. We just simply divide by both, and then divide by this one and over here. Okay, so this is a reverse. What give us the tangent square theta will be 2, right? So it has to be reversed. But simply, as you can see, that tangent scale theta will be a 2. Very simple. So what will be the tangent theta equal to? What is the theta? Well, let's try to get some tangent here. So arc tangent, arc. No, not just a tangent, right? A tangent, and the sorry, this is not the 2. This has to be a root, right? So square root 2. This arc is, I guess, the radian. So we need to change the degree. Oops. Degree. We change this radian into a degree. And giving us the simply degree, giving us what? 54.7. So approximately this is a 55 degree, okay? This is the most important angle when you design the hydrogen pipe and hydrogen tank using the carbon fibers, okay? 55, okay, 55. So I will draw the so 55 will be something like, okay, this is the 45 line, and the this is the 0 and the 90. Now we draw this one. The sigma 1 is the this much can be represented represented. That now sigma 2 will be twice longer, right? As you can see here, this is the twice sigma 1, and this is the divided by half. The sigma 1 is the half, and the sigma 2 is the twice, and then the sigma 2. So I try to draw the represent the magnitude like that. So my point is that okay, this is a larger and this is a smaller. Then the fiber, if this is a 45 direction, then this arrow should be the same, right? But this arrow is the larger, then this fiber direction will be something like that, right? Is a effective direction of a fiber, as you can see that. So that's why we have a 55 degree, simply because this is the 2-to-1 ratio. Okay, 2-to-1 ratio. Or you can say this is a 1.5 magnitude, regardless of a pressure. So that's why the 55 degree, and I hope it helps you to understand or remember this 55 degree. So the point is the older fiber will go in this direction. And the minus, same thing. Okay, so the that's why we have a 55 degree. So when we wind the tank or pipe, and always please remember that this is the 55 degree angles, and the okay. Now let's say that's how we design the angle. Now, how about the stress? Well, stress is like the let's say sigma F reach the fiber strength. You know, the fiber strength, I would say XF, fiber strength. Please keep that in mind. XF is the fiber strength. And the when it burst, I would say the fiber reach the fiber strength, right? And then you can see that this is the how much pressure we can reach. So we can simply we can use a this equation or bottom equation is giving us the same thing, but the important point is that the I would say pressure times, sorry. Now R over T, that's the what we like to design. What the heck? Let's use the bottom equation. So this is also X, and then this is X, F. Okay, this is a fiber strength, and divide by the P. Now what do we have? Sine square theta. And sine square theta, we already know the theta. So the P, I would say maximum. And how much pressure we can reach is that we can calculate. The P max is that XF divided by the R over T, and then sine square. This is the again very simple and very powerful equations, and then we can have go here again. Sine square. What is a sine square? Well, we can simply type here sine, and this is the angle, but we need to change it to this one again, the radian. Right. Okay, so this is 67. Okay, so the 0.6, I would say 0.667. Okay, 0.67. Actually, this comes from I would say the 9 right? Yes, 6 over 9 or 2 over 3. Oops. So this is simply 2 over 3. Okay, 2 over 3. So this one again 2 over 3. When we design using the 55 degree, and this we know that now this is the you can design and then this is the P pressure maximum. As you can see that if this is smaller and smaller, we can have a larger pressure we can have. Okay, so this is a very important equations you can use when you design. So let's say if you like to design 350 bar or 700 bar, of course you need to multiply by the safety factor. Safety factor you can consider 2.5 or 2.25, something like that. If you design the 700 bar, this will give us the 1.5 approximately, let's say 1,600 bar, which is the 160 megapascal, right? So this is a given. Now you can have a R over T. I would say R, let's say you have a humanoid like this, and then where can store this hydrogen tank? Let's say you use the certain part here. Then this, I would say, radius, this is twice of radius. And the point is that how thick the T should be. So the thickness can be determined from this equation. Again, I'm going to rewrite here, R over T equal Pmax. Pmax is the one you design. Let's say if 300 bar is given, this will be some safety factor. And this is the procedures. So the and this XF and this is the 2 over 3. Now, what is the XF? This is the fiber carbon fiber strength. We can always say what is the strength of carbon fibers. Well, the about the 3,000 to 7,000 megapascal, stronger than steel. Steel is about the up to 500 megapascal. So anyhow, I would say is ranging depending on the carbon fibers. We can be very conservative. So let's say 3,500 megapascal. So back to here, 3,000. So this will be 3,500 megapascal, and this can be 1,600 megapascal, right? The bottom one, and then 2 over 3. And you can see that this is about 20, right? This one and this is about the 20 times 2 over 3. So this is the 43. So it's about 13, okay? About the 13 ratio. So you decide the R, let's say the R, well, R, I would say about 5 centimeter, okay? 5 centimeter. Then T would be what? T would be 5 divided by 13 will be about 4 millimeter, right? So this is a simple way to calculate, but very powerful and pretty much accurate. And now about the length, you can decide it, the length, right? This is the length. And you need to calculate the weight of the this tank, right? what is the weight of this tank? Well, you need to calculate the volume. Volume will be a certain volume here. Okay, volume of this tank. So a volume of the, volume means that this one, not inside, the volume of this material and times the density will be giving us the tank and the weight of the tank. Now here, we assume that XF as the fiber strength, but as you get back to here, see, this is the carbon fiber, but there is a certain gap between the carbon fiber. This is the filled with the epoxy. See, this is the some sort of a gap and gap and gap. So the this fiber take over some space, and this gap take over certain space. So total volume and the fiber volume is about 60%. Okay, so when we calculate it here, you need to multiply because the load is not totally carried by the carbon fiber, so you need to multiply the 60 times because of a volume fraction. So 60%, 0.6, and then everything you need to have a 0.6, right? So so rather than 13, this should be about what? About a 8, right? Because we have a 6 here, or we can say okay, 80 will be about is okay. So rather than let me double check. This is the 0.8, 0.6 times 350. So 3,600. This is 1,160, and we have to consider the 0.6 and twice. So let's say this one is 20, and this times 0.6 and times 0.6, and then so this one 2, and rather than 13, I will say yes, it's right, about the 8. So this has to be 5 divided by 8, and then this is what? This is the about 6. Well, what the heck? Let's say 6 millimeter. When we have a 50 millimeter radius, we will have a 6 millimeter thickness. So that's the we can calculate the tank and this. Now, of course, the most important. This is how we design the thickness, and then how we calculate the weight, and now the volume. Since we have a radius, and then how much the this is the 700 bar. You can see that how much the hydrogen we can have, considering the hydrogen density. We remember 0.04 kilo per liter of the hydrogen. We need to double check. But anyhow, this is the very simple but very powerful way of designing the hydrogen tank. Now, the key point is that we have to decide the radius. Radius can be dependent on the where you put it in here, or you can put inside the belly here, the humanoid, and then you can decide. But remember, this the shape has to be a cylinder, because all the theory is the like the cylinder. Okay, well, I was gonna go through all the procedures of the designing of a hydrogen tank, which was assigned to the one of the homework, right? The homework. Here, estimate the size of a mass of a fuel cell. Fuel cell is the power, and then here is the hydrogen tank, the diameter and the length and its mass. Design of this one. I was gonna come to this point, and then this one is not also can be we can estimate the size and mass of a fuel cell. Fuel cell, most important point is the power, and then power can be, determined considering the action and movement of the hydrogen humanoid. That was we covered here. Total energy and total power. Well, very importantly, we need to compare the hydrogen system and battery system. Will be very interesting for you to get used to this kind of a comparison and then propose to any application such as the humanoid and also say eVTOL and drone and many different cases. So this will be the end of today's class. This can be a one-time project, by the way, applied to hydrogen and the humanoid, but can be applied to other system, eVTOL, and any structure you can choose. Okay, this will be again the I would say hydrogen eVTOLs, say design of a hydrogen tank for the eVTOL. That is the one very challenging task. I know it's a very challenging task, but as we went through, this is the kind of a concept we need to have, and it's gonna be a term project assigned. But all the procedures will be similar to these procedures. Okay. Instead of humanoid, consider the eVTOL. Dimensions can be approximated, dimensions can be taken, and the structures you can consider. Say, all the eVTOLs, you have a long bar. Okay, you have a long bar here, and each one you have a motor, and then there's a propeller, all the structures. So this bar can be a storage tank. Okay, I will repeat. This bar can be considered as a hydrogen tank pipe where we can store the hydrogen. And also we can have a hydrogen underneath, like the long cylinder. Don't worry about the end, just consider the line, the cross section and length, and then 700 bar, safety factor, consider fiber strength, volume fractions, and so on. And then first you need to know how much the hydrogen gas we need to store to cover the range of the driving or flying. That is the important. So this is happen to be just open it. You know, the ANSYS finite element method, and it give us the example of powering the future of a flight, designing a hydrogen powered eVTOLs. Well, it's certainly worthwhile to read, but I don't know what they have, but it's important to understand. And then let's explore this example. But the point here, one thing I like to say that this hydrogen tank is stored. Hydrogen is stored in this long beam. Okay. Well, sorry for interrupt. I mean by the internet, and this is the subject I like to cover today. And remember, this is the your term project, and then so go through all the procedures. I will announce when this has to be submitted as a term project. We have several chapters left, but we're not gonna cover whole chapters. Actually, basically, this is what we like to cover mostly in the course. Application is the most important point. Okie, thank you, and then keep in touch through Kato, and then see you next week. Bye.